All right. Thank you very much once again for another meeting. For those who don't know me, my name is Clement. I'm currently a final year PhD student studying mathematics at Cardiff University in the UK, and I'm also a vice chancellor scholar of the university. So basically, the essence of this whole class, online class or free class we've been doing is just to promote mathematical programming among students from Africa, but anyone is also welcome to join. So the key thing is just to learn and then help ourselves to just become good statisticians and data scientists in some future time. So if you've not watched previous videos, so technically we do the meetings on Zoom and then we upload it on YouTube. So if you've not watched the previous meeting, so this is actually our fifth meeting. So if you've not watched the previous ones, it's better to watch them before you start, okay? And then specifically for this video, it's very necessary to watch the recent one, the fourth meeting, because it's just, we are just taking over from there. All right, so without wasting much time, I would share my screen and then explain what we are going to do for today. Okay, so for today's class, there are basically things, few things you are going to look at. So last week I gave an assignment, and then the assignment were a little bit detailed. But so for the first part, I'm just going to focus on solving just few selected questions, and you can just use these solutions to work on the other ones. So the first thing we are going to do is, first of all, for question one, which was just, so the whole of question one was an assignment given last week, and then there were more than these questions, right? So I'm just doing few ones. So first of all, we're going to learn how to maybe extract multiples of 12 from any range. Okay, so you could be asked to find maybe all prime numbers from, let's say, a certain number, let's say from 1 to 1 million. Tell me all the prime numbers, tell me all even numbers, tell me all odd numbers, tell me all multiples of any number. So, and you know that when we talk about multiple of, let's say, 5, it means that there's a regular increment of 5. If you talk about multiples of 8, it means there's regular increment of 8. If you talk about even numbers, we know it starts from 2, right? And then there's a regular increment of what? 2. If you talk about odd numbers, it starts from 1, and then there's a regular increment of 2. So basically, with what we are going to do for the multiple of 12, and we did this last week, okay? So if you've not watched the previous meeting, try and watch. So this is just to answer some special questions. And last week too, we introduced a Monte Carlo simulation. So we said Monte Carlo simulation was originally developed to basically help to model random phenomenon. Okay, so the random phenomenon, anything that deals with random phenomenon, as example could be in games. Okay, so in a game, we don't know, I mean, you could lose or win, isn't it? So at the end of the day, or gambling, or even at birth, anything that has some degree of randomness, you can actually do an experiment using the Monte Carlo simulation. And we said Monte Carlo is nothing strange but trying to, first of all, determine when an event should occur. So you should know specifically how many events you are trying to deal with such that any of them can occur. So you should know exactly the event you are dealing with, and then we'll use a certain random generator. And usually we use a uniform distribution to determine when an event should occur. And if the event should, and when should the event occur to will be dependent on some specific thresholds or some conditions that we would also assign. So basically, so we introduced that last week, and we even did that for tossing a die, and then tossing a die a number of times and so on, just to see which phases are more likely to occur and so on. Fine. And we said that Monte Carlo simulations are more effective when the sampling, or when the simulation is done a very large number of times. Okay, so that's also one thing we have to keep in mind. So for the first, and then the next thing we are going to do is that we already started last week. We already started how to simulate probability distributions. So we did some simulation from exponential population distribution, normal, log normal, Poisson, uniform, and binomial. So these things, if you don't know much about it, don't worry, but just get the intuition and just understand that there's this something we call probability distributions, okay? And I even explained last week that for probability distribution, almost every phenomenon that we do in reality follows a distribution. If we are solving some set of questions, the number of correct answers actually follows a distribution, especially binomial, with some specific parameters. So where the parameters is dependent on how many questions you are solving, and then if you are doing a multiple choice question, and then you know that if there are 5 possible answers, then you have a probability of 1/5 of getting a question correct. So in such a case, we can actually model, or we can actually find probability that a certain number of students will pass and all sort of things by just using binomial distribution, because we know that that process follows a binomial. So the essence of knowing how the distribution of a process is just to help us in situations where we want to calculate probabilities or we want to do further exploration. If we know that the process, for instance, we know that the number of road accidents that will occur at any specific period or amount of time follows, let's say, a Poisson distribution. So in that case, we could always simulate from Poisson distribution if we have a fair idea about, let's say, the mean number of accidents that occurred within a period of time and so on. So simulation is very relevant. Personally, in my PhD, I use simulation for disease modeling as well, to even simulate the spread of movement or parasites across different across a whole population of fish. So simulation is very important, and all we do is that we just adopt the Monte Carlo method. So the Monte Carlo method can be used for any random phenomenon. All right. So what we are going to do there is that first, for the previous assignment, we said that we want to create a Monte Carlo simulation to describe the outcome of for 100 women at birth. And then we know that for the women at birth, they could either give birth to a male or female. And we are saying that, so the experiment should be able to determine when a male born occurs or when a female born occurs. And then we are saying that we know clearly that the chance of giving birth to a male and female are literally the same, right? So I mean, they have a probability of 1/2, or let's say 0.5 of occurring. Okay, so this is just to say that we are talking about unbiasedness in this case. So, but situations where you know that for a certain particular woman, that woman had more chance of giving birth to, let's say, males, because she has been giving more birth to males, then in that case you can make your probabilities a little bit biased. It always depends on what you are doing. But suppose we are assuming that male birth and female birth are equally likely to occur, then they will both have probability of 0.5 of occurring. And then we are going to record among the 100 women, how many actually gave birth to male borns, and then how many gave birth to female borns. And then we would also try and plot their proportion and increase the number of women to 1,000, and also compare the findings with that of the 100. So with this particular example, you should be able to use this. I wouldn't advocate for those who have been doing lottery, but technically, suppose we have 100 numbers, okay, 100 numbers from 1 to 100. And then let's say you want to select, and let's say you've checked previous occurrences in, I mean, I'm not going to talk about lottery here, but basically what I'm trying to imply is that you can actually use a Monte Carlo simulation to check which numbers are more probable to occur if we assume that each number has equal chance of what being selected. So if you want to select maybe 3 out of 100, or you want to select just 10 numbers out of 100, you could explore, I mean, using this technique. Okay, so I wouldn't go much into that. Fine. So the next thing is we are going to prove a certain powerful theorem, and it's actually the most powerful statistical theorem, and it's called a central limit theorem. And then we will do that based on the means. You can actually do that for other cases as well. And then when we are proving that, we'll be making use of some probability distributions that we did from the step 2. And then the next thing is that we will also introduce some important techniques called bootstrapping and Jackknife estimation techniques. They are also a sampling scheme or a resampling scheme. There are other resampling schemes. One is also, which is also very powerful. We call it hypercube sampling, okay? But for now, bootstrapping and Jackknife are very important. And the reason why they're important, I'll explain to you shortly. And you find out that they can help you to improve upon your estimates, okay, of any data. For instance, it could be you are finding the average number of something, or you are finding the mean, any particular estimate you are dealing with. It could be proportions, it could be anything. And at the end of the day, it will help you to be able to bound your estimate or give some degree of confidence, or maybe some prediction intervals around those estimates. And if you know the true parameter values, you could also compare your estimate with the true parameter values by computing something we call bias. Okay, so we will find all these things by the end of the meeting. All right, so let's just go quickly. Because we've already done this, I'll just explain each line of code here, and then I'll just move to the next. So I'll speed up a little bit. So the first thing was that we wanted to extract multiples of 12. So this was a previous assignment. We wanted to extract all multiples of 12 from 10 to what? 10 to 100,000. So the first thing we did is that we said we want to do that first of all by using a for loop, and afterwards we should also use a while loop to still achieve the same results. And then we said that we'll have to learn how you can save your, and don't forget that if you are using loops, you should be able to save your results. Okay, so the reason why you save your results is for you to use it at a later time. So if you want to use your results at a later time, it's always good to save it. So we can also save it as a vector, as a list. Technically, we can even save it as a matrix. We can even save it as a data frame. So now I've introduced how to save it as a vector as well as a list. So the first thing is that we create that sequence from 10 to what? From 10 to 100,000. Now I told you the last time that this sequence, I could have also have created it by just writing sequence 10 to the 100,000, and that is enough. Or I can add by comma by equals 1. So by equals 1 implies that you are creating a sequence from 10 to 100,000, but you want the regular increment to be 1. And if you don't include it, if you don't include this part, by default, bar is equal to 1 in the sequence function. Okay. If you want it to increase by a regular interval of 2, you just put 2 here. All right, fine. So first of all, to save it as, we are doing it to save it as, save the results as a vector. So as a vector, I told you there are so many ways. Here you can either replicate any string. So here I could have just written my name, and I'll still run and get the same, and everything will still work. I'll get the same results, okay? But basically, I'm just using NS. I'm using, so you can technically use anything if you've watched the previous video. And then with this, I could have also created a sequence of zeros. So what the rationale is that anytime you want to save results from a loop, you need to create a holder. So by creating a holder, it means that you have to first of all create a certain sequence of let's say zeros, or a certain sequence of a string, okay, or sequence of NAs, such that now once you, for each loop or for each realization, if you get the results, it goes back to replace the NAs or the zeros that you originally created. So basically you need to create a holder. Okay, so that's basically what this is doing. And then here we are saying length of n. So n, you know that n is actually a vector from 10 to 100,000. So the length of that will just give us how many observations or numbers are within that sequence. So basically that's what I'm doing. Okay, and then so here, so first of all, I'm saying that if for I in sequence along S. So the last time I told you, if I should run sequence along N, what it does is that even though we know that the first number was starting from 10 to, so it was 10 to this, sequence along will return their positions or their indexes. So it meant that the 10th number is technically the first position. So always, instead of using for, I could have used for I could have used for I in, let's say, 1 to length of n, okay? And that will give me the same thing as just writing sequence along n, okay? So keep that in mind. So it's smarter to just say sequence along n to just to extract all the unique positions, okay? So here, what it's doing is that you realize that I'm not putting if I, but I'm saying that if n with this square bracket. I told you that if you have a vector, we use the square bracket to extract, okay? So what this is saying is that if when I, so this is how the for loop works. So if first of all, consider when I is equal to 1 here, okay, because the sequence along n, you saw that it's actually from 1 to a certain number, right? So it's just the positions of each of the numbers from 10 to 100,000, okay? So here what I'm saying is that if the ith number, so the I is the position, so when I is 1 and you put 1 here, it meant that you are considering the first number in the sequence 10 to 100,000, which is 10. So it first of all would ask if 10 is, and I told you that we use double percentage sign, okay, as to find what we call modulus or remainder, okay? And we said that if I consider, let's say 4, 4 is actually a multiple of 2. Why? Because when you divide 4 by 2, your remainder is going to be what? 0, or the modulus is going to be 0. So it means that whenever you divide a certain number by a certain divisor, and at the end of the day, you are getting the remainder being 0, then it means that the divisor was actually the number itself is actually a multiple of the divisor, right? So basically, so that's what we are doing here. So here we are considering the if the number in the sequence, okay, divided by 12 is actually giving us a remainder of 0, then it should what? Save that number inside the holder that we created. So don't forget that we've created a holder. If you check the length, let's check the length of this one. So basically the length of this is 99,991. So basically, so what it's doing is that it goes to so after satisfying the condition, then it will save into the fold into the it's going to replace the NA that was originally created in the first position. Then when I is 2, then it checks whether the second number, or the number in the second position divided by 12 will also give a remainder of 0. If so, then it should save. Okay, so it means situations where that condition is not satisfied, there'll be NA still left, right? So for instance, let me now, so basically that's what we are doing here. Okay, so now if I try to run this, let me just select few let's say the first 10. So let me take this out. So if you look at the first 10, you realize that the first when it checked when n is equal to 10, since it didn't satisfy this condition, nothing came to what? It didn't replace the n's. So, and it checked when it's 11, when n is 11, it wasn't a multiple of what? 12, but 12 was the first multiple of 12, and then it replaces that na. So it does. So that's actually the mechanism with which it works. So basically that's for the mechanism. So let me paste what yeah. So here the NA dot omit, what it does is that it takes away all the NAs and keeps the actual numbers. Okay. So basically now let me run this. Okay. So now here, so first of all, if I take all the NAs, the actual sequence, the actual vectors left would tell me exactly how many multiples of 12 are there. So if you realize that here, if I find the length of now the multiples of 12 after eliminating the NAs, it tells me that there's technically 8,333 multiples of 12 that are from 10 to what? 100,000. So with this technique, you can find any sequence within any range, the number of any sequence, the number of even numbers. If it's even numbers, all I need to do is just to replace this 12 by 2. Okay. If so basically that's the motivation for that. And then so these are the first 100. So with this, I've extracted the first 100 just for you to see the first 100 multiples of 12. Okay, so I did this by storing the results as what as a vector, where it replaces the NAs when that condition is satisfied. If not, then it doesn't. And then I just have to remove all those NAs so that I get what I'm interested in. Secondly, I said you could also save it as a list. So for the list, there are several ways. You just write list in bracket, that list with the empty bracket. So it's the same thing. I just copied the same thing here. All I did was just to change instead of numeric, or instead of replicate NAs, I just use list. Okay, but don't forget the difference is that for the list we use 2 square brackets to extract, but when it's a vector, when you are saving as a vector, we use just a single square bracket to extract. So keep this in mind. So don't forget that here I'm using a single bracket because at the moment n is the vector. Okay, that's the sequence, and I'm saying that once the condition is satisfied, then it should save the number at the ith position. Okay, into the holder that we created. But here, when you come down, what we are saying is that if this condition is satisfied, okay, so it should now go and replace, or it should save in the ith list, Okay, so at the end of the day, the list or some list will not have values, isn't it? So what you do is that writing on list around this one, or on list of the list that you created, would actually convert it to a vector, and that's what we are seeing down here. And then it will also remove all NAs that, sorry, it will remove all the NAs that existed in the data. So technically, here I just used on list. I didn't have to use NA.omit. If I had used, let's say, C concatenate sign with an empty bracket, it will also do the same thing for us. But in that case, let's try that and see what happens. So if I use just a C, okay, and then I run, let's say this one. Let me just extract. It's a list. So for a list, let me just run this. Okay. Now let me take this. Yeah. So basically, so the C also did this. The empty C also did the same thing. Even with that, let me take this off. Okay. Yeah. So with the C, even without the unlist, it still worked. Okay. So, but so you can always unlist it or not. But situations where you need to unlist it to get the vector, you just do that. But you could have used the C, or you could have used list with the empty bracket. Okay. So that's basically that. And then you'll be able to know. So it's just the same as the previous one we did. So let me take this off. Let me run this. Okay. Fine. So the next thing was, how would you use a while loop to do? So the first two is this for loop I'm using. Just I was showing you how to save it as a list and also as a vector. For a while loop, you don't have to first of all create the sequence. If you remember in the previous one, we had to first of all create this sequence. Okay. But in the for loop and in the while loop, what you need to do is that, what is your last number? Okay, so here you can also save it as a vector or as a list. So here I'm just doing for a list. You can try how to save it as a vector by using the previous one I explained. So all you need to know is that, what is the last number? So the last number is 100,000. Okay, fine. And what is the first number? So it's the first number you always have to start. But how would you get all the sequence up to 100,000 is dependent on this one. So here, what it means is that for n is equal to 10, right? That's the first number. So there's a condition. So don't forget, for the while loop, there's the syntax. I already explained it in the previous lesson. If you've not watched that, try and watch that. So for the while loop, what we say is that if the number that I'm considering is less than the last number, then it should continue on and do what is happening. Okay. At the moment, if I choose any number that is greater than the last number, nothing would occur. Okay, so here, once you start a number that is less than the last number, then it will now go on and check whether it satisfies the condition. So it first of all picks 10. Is 10 less than or equal to the last number? If so, then it now check, is that number a factor of 12? If that number is a factor of 12, then it should store that number in the list. So here, that's what I'm saying, that you could have also created, you could have just created a vector. If you wanted to create a vector for it, you could have also created let's say, numeric. If you can use numeric to create a sequence of zeros, and then you can use length in bracket n. Okay, we already know the sequence that we did up there. Okay, so you could have used that and use just a single square bracket here, and that would just do the magic for how you would save it as a vector. But bear in mind that afterwards there will be NAs. In this case, I was using sequence of zeros. So there will be zeros, which so usually using the numeric is good, but I would want you to use replicate NAs instead. Okay, fine. So that at the end of the day, those that has NAs means that they were not factors of 12, and you can easily use NA.omit to remove all those NAs. Okay, so basically this is how we use the while loop to achieve this. All right. So let me go straight to the Monte Carlo question. So first of all, like we said, so what I'm doing now here is that I'm creating a Monte Carlo simulation to determine the outcome of birth, whether a male born or a female born, for a single mother. When I'm done, then I'll do for 100 mothers and I'll do for 1,000 mothers. So for a single mother, this is what we do. So first of all, I have to create something. I'm calling it count. Okay, so I'm creating, and don't forget there are two events we are dealing with here. either male birth or female birth, right? So here I've created a sequence of 0, and specifically it's just 2 zeros, a vector of 2, a vector with dimension what 2, which is just zeros, okay? And then with that, so I could have used replicate 0 twice, or I could have just used numeric in brackets 2, and it will do the same thing. So for instance, if I should copy this and create a cell here and run this, it's just, so I'm just creating like I told you that always you need to create a holder or something that will hold the results you want to save, isn't it? So that's basically what I did here. So fine. So here I'm not saving the outcomes, but I'm rather saving how many instances that female birth occurs and how many instances that's male birth occurs. Okay, so basically that's why I needed to just create these two a vector of just of size 2. Okay, so what I'm doing here is, this is the most important thing. So this is something called the uniform random variable. Okay, so that is what we are using to so the uniform. So if I should run this one, you realize that this is creating or simulating or trying to determine values between 0 and 1. Okay, so if anytime I run, you realize that I get a certain probability. Okay, so here what we are saying here is that I could have just used if. So for I in rand, so the rand here is the value that is selected. So I'm saying that for any value that I get after running this, okay, if that number is between 0 and half, okay, it should count the number of boys and print it out. Okay, so the count here plus 1 means that originally I made the first value of count to be 0, isn't it? So the very moment this condition is satisfied, it should add 1 to the previous 0. If the condition is satisfied again, the count is now 1, then it will add another 1 to make it 2. So anytime this condition is satisfied, it will keep increasing the count by how many times the condition was satisfied. Okay, fine. And then here I said if else, okay, if the the number is between half and 1, then we have a girl occurring. So you realize that I needed to use a random generator and decide with what probability should each event occurs. Okay, so with this one, I could have just used if I is less than half, like less or equal to half, and it will still give me the same results. The reason why I brought this one was just to show you how you can write more than one condition at the same time. Okay, so here I'm saying that if I is greater or equal to 0, and so here I could also use a single n sign and a single n sign, and it will give you the same results. So at the moment, you realize that anytime I run, so it means that if I run this, it means this particular woman gave birth to a girl. If I run again, the woman gave birth to a boy. If I run again, boy, and so on. So this is, and so if you can see, this is just a way of trying to mimic a real system, or trying to mimic in reality the chance of giving birth to either a boy or a girl. But here I've considered n equals 1. N equals 1 means that I'm considering what? I'm considering only one woman. If I had considered n equals 2, see what happens. So n equals 2 will give me two different probabilities, where the first one is for the first woman and this one is for the what? For the second woman. So the number of times you increase n will determine how many women or cases you are considering. Okay, so don't forget that. So to do for the 100 women, all I need to do is that I just have to come down and then change the n to be 100. I've done nothing again to it. Everything still holds. All I needed to do was to change it to 100. Okay, so now let's run this. So after running that, now I can check how many boys. So if I just now run the count, because I told you that this count is such that anytime this condition is satisfied, it increases the count by 1, right? So here, if I now run the count, it tells me that there were 55, in this case, there were 55 males and then 45 female births, okay? So I just use this for loop to print it out well. So now here you can clearly see that it tells me that when I considered 100 women, 55 of the women gave birth to boys, and then 45 of the women gave birth to girls. So this can tell me something a little bit. Okay, it doesn't mean that if I run it again, I won't get a different result. If I run it again, this is what I had. So you realize that for 100 women, anytime I run, it appears male birth appears to be more than female, the female birth, okay? All right, so now let's increase the number of women to 1,000. So I have increased the 100 to 1,000. Now, when I run, this is what is happening. Still, boys are more, okay? And here, the girls became more at a particular run. So you realize that this is what we mean by randomness, okay? And if I want to get the same results anytime I run, I can set seed, set dot seed. Let's say any number. So you can put any number. The reason why we set seed is that if I should send you these codes and you want to get the same results, excuse me, the same results that I had. Once you use the same seed number, if you run, now look at this, the boys is 520. If I run again, it's still going to be the same, right? Because I've set a seed. Okay, let me just ignore it. And now let's just, so at the moment, the male births are more than female births, okay? And then suppose if you knew that in a certain hospital or among a certain group, it could be ethnic group or something, male births are more likely to occur, then you can now specify the exact probability that you think that male births are more likely to occur. Specify that probability here, and then you'll be able to get something that mimics that system in a more realistic manner, okay? So at the moment, for 100 births, for 1,000 women, this is what we are getting. So it appears that males are more likely to be born in this particular experiment. So here, I just use this to create a bar plot where I am now. So let me just run it now. So at the moment, okay, let me bring this a little bit down. So let's say 0.4. Okay, so at the moment, what this is telling me is just a bar plot. So this is just a bar plot specifying the sex of baby. So we have boys and a boy and girl child. And then this, I just pasted. So these functions were just to paste this, and that. So it's pasting in percentage wise, the percentage of male births, okay? And the N is just telling me the actual number of boys and so on. Okay, so that's just the Monte Carlo experiment. And you can use this Monte Carlo experiment for anything that you think has some degree of randomness, okay? So next time you should be able to use the same thing that I did exactly for the male, for the outcome of pregnancy. You can use it the same thing to consider experiment of tossing a coin. You see, when you toss a coin, you can either get a head or tail, and each is equally likely to occur. So all you need to change is just to change the print boy, change it to head and tail, okay? And then it's the same kind of experiment, okay? So don't forget that. All right, so now let's switch to our main topics of today. So the first thing is we are going to talk something about central limit theorem. Now, if you've never heard central limit theorem, let me just explain what central limit theorem is. And don't forget, I will share the codes, everything will be uploaded on Piazza. So this what I'm using is what we call Jupyter Notebook, okay? So for Jupyter Notebook, I think is the best thing you can use to be running R. And I've explained its importance that for supervision wise, I mean, you can, because the results are there, you can even make notes whilst you are still seeing your plots, everything will be there. If you are using RStudio, unless you save your results into your repository, and I've explained how you do that in our previous videos, so that shouldn't be a problem, okay? But I think Jupyter Notebook is very important. So next week, there'll be a whole session. Next week, we are not going to do anything on statistics for next week or modeling. Next week, we are just going to learn how to use Jupyter Notebook. Okay, so that's actually, so by the end of next week, you should be able to do the things I'm doing also on your computer. Okay, fine. So that's what we are going to do next week. So what's the central limit theorem stating? So what the central limit theorem is stating is that the mean, so here we can just look at this, but I want to state it in my own way, and I'll explain it in my own way. So what it's saying is that the sampling distribution of the mean would always follow a normal. So here we are not saying follow a normal, but approach. Okay, we are not saying that it will be exactly normal per se, but approaches a normal distribution. Okay, and in some situations, when you do the sampling a large number of times, then it can really converge to a normal distribution. But so what we are saying is that when I talk about sampling distribution, it's just the frequency distribution. So what we are saying is that sampling distribution of the mean would always approach a normal distribution, okay, as the sample size gets larger, irrespective of the distribution of the population. So it's possible that there's a certain population which follows, let's say, Poisson distribution, okay, but after finding the sampling distribution of the mean, you might get something that is converging towards a normal distribution. Now, let me explain it now in lay terms. So what I just stated is a more technical term. So I'm going to make it very simple for everyone to understand. But keep in mind, in statistics, when you talk about large sample, 30 or more is what we use to define when we say something is large, okay? And don't forget that. And there were people who were making this mistake in research. Sometimes they have a data and the data has a size, let's say 50. And they will say that because our data has size of 50, then our data is normally distributed. It is a statistical suicide. It is wrong because they are trying to interpret central limit theorem in a wrong way. Central limit theorem is talking about the sampling, or is talking about the distribution of the mean, not the data. So what we are saying is that if your data, or let's say your data you are considering has at least a sample size of 30 or more, okay, and is done a large number of times, which I'm going to explain shortly, then the distribution of the means for each of the samples is what is going to follow what, or appear to converge to a normal distribution. But we are not saying that if your data set is, let's say, 30 or more, then the data itself is normally distributed. No. And people have been making this mistake in so many studies where they just conclude that since the data is more than 30 or large enough, then it means that the data is normally distributed. No, that's not what the central limit theorem states. So now let me now break it in layman's terms. So what it means is that suppose I consider, let's say, a certain sample, and the sample is having a size of, let's say, 30. And I consider, so call that sample one. Like sample one is like a sample of values, okay? And these values are coming from any distribution, and then they are just 30. Then I consider another sample, and I'm calling that sample two. And it also has a size of 30, okay? And I consider another sample three. So what he's saying is that for each of these samples, they are having size of at least 30, isn't it? Let me find the means for each of the samples. So when I consider sample one, I find its mean. Then I consider sample two, then I find its mean. Then I consider sample three, then I find its mean. Now, if we do this sampling a very large amount or number of times, so suppose I do this sampling about 10,000 times. If I do it if I consider 10,000 different samples, okay, 1 million different samples will perform better than 10,000 different samples. So as if I consider just 100 samples, 1,000 samples will do better than the 100 samples. Okay, so keep in mind that the central limit theorem only what makes sense if you consider asymptotically large samples. So if you consider large samples, then the central limit theorem in terms of the convergence to the normal distribution becomes a bit clearer, which we will see clearly. Okay, so what I'm just saying is that let's say we have sample one and it has data points with only 30 data points. Then I consider another sample. For each sample, find a mean. Find the mean for sample one, the mean for sample two, the mean for sample three, up to the 1,000 or the 10,000 sample, okay? And then plot the means. If you now plot the means, don't forget that those means that you've gotten, the means for each of the samples is what we call the sampling distribution of the mean. And if we should plot the means, the distribution will look like a normal distribution. And this particular theorem is the most powerful theorem in statistics. Okay, and it is through this theorem that you find out that when you are doing hypothesis testing, you will hear something about test statistic, and every test statistic, okay, actually has a distribution. Okay, and most of the most of the distribution for instance, if you are doing t-tests, okay, for t-test, for instance, okay, you find out that for large samples, the distribution of the mean will follow, or the test statistic actually will follow what a normal distribution, okay? Unless the sample size is small, then it follows a t-distribution. Okay, fine. So just keep in mind that distribution of those test statistics were derived based on the central limit theorem. So it actually, central limit theorem help us to deduce or to actually derive the distribution of some test statistics for some hypothesis testing, okay? So it's very useful, and it's actually the most important theorem in statistics. All right, so what I just described, we are going to create or we are going to actually do a similar experiment where we want to prove what they are saying is true. And let's see what I found. Okay, so what we are going to do is that we are going to consider, let's say, exponential distribution. Simulate 30 data set from exponential, another 30 from exponential, another 30 for exponential. Let's say a large number of times, about 10,000 times. And we'll find means for each of those exponential samples. And when we are done, we'll plot the distribution of the mean, and then we'll check whether indeed the distribution of the mean looks like a normal distribution. That is basically what we are going to do. And if you do for exponential, we also do for normal, log normal, Poisson, uniform, and binomial distribution, meaning that the theorem, if it holds, is because they said irrespective of the distribution of the population. So it means that whether it is a discrete distribution like binomial or Poisson, it should still hold. So let's check whether indeed it holds. And let's see what I found. Okay, so what I did here was, first of all, so last week we learned how to simulate data from these probability distributions. So I just copied last week's code. Okay, so if you've not watched the last week video, please try and watch the YouTube video for that. So here I'm simulating from binomial, 1,000 samples of binomial with these specific parameters, and then 1,000 from Poisson, 1,000 from uniform distribution, 1,000 from exponential, 1,000 from normal, and 1,000 samples from what? Log normal. Okay, and so here I just run, and then I'm just checking the original distributions of the data itself. That is why if you go and tell me that your data set was, because look at something, I considered 1,000 samples, but if you look at the distribution, can you tell me whether you are seeing anything normal in here? The only thing you see to be normal was the actual normal distribution. That's the only thing that appears to be normal. All the other ones I considered. This log normal behaves like exponential. It has high occurrence occurring at the lower value. So you realize that it is very skewed to the left. And then smaller values of log normal samples have higher chance of occurring. And it's the same thing for exponential. Distribution. Okay, so these are typically a skewed distribution, positively skewed distributions. So if you tell me that you have a data, and because your sample size is 30 or more, you realize that a sample size of even 1,000 for exponential is not normal. So suppose your data was fitting an exponential distribution, and you were telling me that according to central limit theorem, like we're stating it wrongly, that central limit theorem is saying that if my sample size is 30 or more, then my data is normal, then it's a mathematical suicide, okay? Because the normality we are talking about is about the distribution of the means that has been obtained after finding means for different samples a large number of times, okay? Fine. So originally you can see that it's only one variable, or only one distribution, which is normal, which is the normal distribution. By normal, I mean that you realize that the curve looks like the rate at which it switch it extends to the left and right are literally the same, and it looks like a bell shape. Okay, it looks like a bell shape. So that is how normal distribution looks like. Look at uniform, and look at exponential, and look at, and for the discrete samples, sometimes you can see some zeros occurring in between. Like, so here, if we see there wasn't any value here. Okay, so because it is discrete, so it's just recording when the sample is equal to 0, when the sample is equal to 1, and so on. But the discrete ones, it could be 1 point something, 2 points. I mean the continuous ones, it could be 1 point something, 2 point something. So always you get something a little bit continuous. You won't get any situations of discontinuity between when you do the plot. Okay, but for the discrete cases, you can get some discontinuity, as we are seeing in here for the Poisson, for instance. Okay, so now let's go straight. So now we are going to now prove the central limit theorem using just exponential distribution. So ideally, exponential distribution is not normally distributed, as I've already explained to you. But I want to see that if I consider different exponential samples, and I should find the means for each of the samples, and I should plot the means, I mean the distribution of all those means, it should look normal. And that is what the central limit theorem is saying. Okay, so let's see what I did. But the smart way I did was that I wanted to write the function to do not just for exponential distribution. So let me say from different probability distributions. So a good programmer is not someone who writes different codes for different tasks. A good programmer is someone who is able to write a single code to still do a lot of things at the same time. And that's basically what I'm trying to do here, okay? So what I'm trying to do here is that I'm first of all simulating 100,000 different samples, okay? And then the different samples, don't forget that each sample should have size, let's say 30. So here the condition is saying 30 or more. So I'm just considering the least value. So that if even the least value is holding, then it means that if now you consider samples, let's say 100 for each sample, if the size is 100 and you still apply the central limit theorem on it, then it will easily hold. but I want to use the 30, which is the least value it should hold. Okay, so that if it holds, then great. It means that if you actually increase the size, each sample size above 30, then you should get even something much more powerful, isn't it? Fine. So here I'm considering simulating, let's say, samples of size 30 from exponential, but I'm doing it 100,000 times. And I'm doing the same thing for Poisson. Each sample from the Poisson should be 30 of size 30, 30 samples or 30 data points. But I'm doing that for 100,000 different occasions. And don't forget that for each of the 100 different occasions will have different values, okay? Fine. So here is just the names of the distribution, and here I'm creating a vector, a list, okay, to what? To save each of the samples. And the reason why I'm creating a list so that I can save each of the sample is that there will be a situation where I'll be plotting, okay? But when I'm plotting, I don't want to create separate lines of code for each of the distributions, or separate code for the sampling distribution for each of the probability distributions. I want to use a single line of code using for loop to get all those results at the same time. And that's actually what a good programmer does. So just keep in mind that by the time we end the whole of our lessons and by the whole of this class, not just today, I'm talking about we are done with everything, you should be able to find smart ways of writing codes to do more complications at the same time. And that's actually a good thing that you should be able to do. Okay. But at the beginning, you can do the separate things, a different lines of code for different things. But as time goes by, you should try and see how you can do things together. Okay, fine. So here I've created a sequence, and I've created, don't forget the length of the names will return how many probability distributions I'm considering here. So there are 6 distributions I'm considering here. So this is generating 6 different lists. Okay, and now for each list, keep in mind that you can have a list and still create a list of a list. Okay, and you can also create a list of a vector. So what I mean by a list of a vector is that, you see, now I've created different lists. Okay, so instead of trying to use a certain object name, I could have just written exponential underscore samples. Then I'll come and write Poisson underscore samples. But when I do it that way, I cannot use a for loop around all of them and get the same, get all the different plots at the same time. So instead of using exponential samples, I want to use a name called probability underscore sample with, and then extracting one will give me for the exponential. Okay, so now I've created a list as an object name. So I could have just written exponential underscore samples. Okay, and then, but if I do that, I cannot do the other things I said. I could combine all the results at the same time and get the plot. Okay, so this is like an object name I've created, and I'm saying that for the object name this, I'm creating another list for the list to save all the different 100,000 replications I'm considering, okay, or repetitions I'm considering. So here I originally created a list as an object name. Okay, that's what I said, that create 6 lists as an object name for each distribution. And here I'm now creating another list for each. So you could have created a list, which is the first case. And for each list, you can create sequence of vectors. So mean that each list can also take up a vector. Each list can take up a data frame. So lists are very powerful. You can use lists to store data frame, list to store list to store vectors at the same time. Okay. So here, that's basically what I'm doing here. So here I'm creating a list of a list. So that's why I brought another square bracket. So you realize that all this while we were seeing double square brackets. Now, because the first one was a list, I needed to bring another double square bracket because I've created a list of a list. Okay. So now at the end of the day, what this is doing is that for the first object, okay, the first object, which is actually exponential, that's why I put 1 here. 2 here means that we are talking about Poisson. The first 3 here means we are talking about uniform, and so on and so forth. And the 6 is binomial samples. So here, the K here is representing the many times we are doing the replications. So here I'm considering from 1 to what? 100,000 replications, okay? So here, the very moment you put, let's say, let me create a file here. So suppose I run for, let's say, I in 1 to, let's say, 10, okay? And then I write, let's say, print, let's say, So here I'm trying to print, let's say I'm trying to simulate, let's say Poisson distribution. So R Pois, okay. I'm considering just 10 samples. Okay, let me use 5 samples. Okay. And then let's say the rate is, let's say 1, fine. So here, see what happens. So you realize that anytime I use a for loop around the same function, you see, I didn't, so anytime you want to create, let's say 10,000 different Poisson samples, I just have to run the function 10. So if I want to create 100,000 times, I just have to run the function 100,000 times. So here you realize that I ran it 10 times and I'm getting 10 different samples from Poisson distribution. So that's basically what I'm doing here. So here I'm running it 100,000 times and it should save each of them. Okay. So here at the moment, I'm not saving the results. So that's why I'm using another list to save each of these. I'm using another list to save each of these. So basically that's what the second square bracket is doing, to save each of the replicates that I'm doing, like the 100,000 times. Okay. So then you just run. Okay. So when I run now, I told you that the first extraction actually represents when here is 1, it means exponential. When it's 2, it means it's Poisson. Okay. So here I'm considering 1, but I want to view the first 30 samples. Okay. I'm talking about the first exponential samples. Don't forget that for each sample, I'm creating what? 30, right? I'm creating, so meaning that I'm creating 30 samples from exponential, but I'm considering 100,000 different replicates. Okay, so that's basically what we are saying. So here, this is just to extract the first one. So here, when I is 1 is exponential, and extracting this will give me the first replicate. Okay, and here, still when I is 1 is exponential, putting 2 here will give me the second exponential sample. Okay, so if you want to see the 100,000th one, I just have to put 100,000 here and then type 100,000 here and I'm good to go. Okay, fine. So let me just continue. So you can now view for, suppose you want to view for binomial, you just have to put what? 5 here. So if you want to view the first replicate or the first realization for the binomial, you just have to put 6 here and you put 1 to view the first, put 6 here and put 2 to view the second, and so on. And you see that they are different samples. Okay, fine. So now what we are going to do is that for each of these replicates, we are going to find the means of all these, and the mean of this will represent the mean for the first replicate of the exponential sample. Then finding the mean of this will give me the mean of the second replicate of the exponential sample. And we are doing the same for the other distributions. So that's, and I usually love to do a lot of things at the same time. So what I did was I needed to also create another list where here I'm saving the mean distribution for each of the 6 probability distributions. So here I'm also creating 6 different lists. So if I should run this one, okay, if I should create a cell here, if I run this, you see it has created 6 different lists. Ideally, if I wanted to create just a single list, I could have just written list in bracket this, and I could have just written list in bracket like this, and that would create, let's say, a first list. If I want to create more than what? If I want to create more than 1, here, if I want to create 1, I can equally also put 1 here, okay? If I want to create more than whatever, if I want to create 5 different lists, I put that here. I wanted to create 6, so I just have to put 6, okay? So that's basically what this line is doing. So what it's doing is that when I is actually equal to 1. So here we said that for I in the sequence, I told you sequence along the names of the distribution. See what happens. If you remember the names of the distribution, if I should copy it up here and then bring it down. So if I run this one, you find out that these are the names of the probability distribution we are considering, isn't it? But whenever I use sequence around the names, it tells me rather positions. So that's why I told you that the sequence along is better than trying to write I from, because if I had written I from, or I 1 from, or a sequence of 1 to, let's say, length of, let's say, the names. Okay, so ideally, if you Googled or you've seen most of the for loops on YouTube, you see that people have been writing 1 to, let's say, the length of something. I don't want to use that, because you realize that the sequence along gives me exactly the same thing, and it's much more smarter to do that than using the I whatever. So that's why I like to use the sequence along, because it gives me the same thing. So here is the same thing as saying from 1 to 6. Okay, So what it's doing is that, so here I created a vector, right? A list. And here I'm creating a list of what? A list of what? Vectors. Okay, so here you realize that previously I put a list here, okay. I put a list here previously in the previous one I wrote. If you come up here, you realize that I put a list. So I was creating a list of a list, but now I'm creating a list of a vector. The reason is because for each of the distributions, we have what? We have 100. We've done the replication how many times? 100,000 times. So it means that we have 100,000 different samples. And I'm going to find the mean of each of the replicates, or each of the different, the 100,000 replicates. I'm finding the mean of each. So when I find the mean of each, I'm going to get what? I'm going to get 100,000 different means for each of the probability distributions. So that's why I'm creating a holder, which is also creating a holder for the 100,000 different means. So here I'm creating a sequence of zeros, because I told you that anytime I want to save, I have to create a holder, whether create a list or whether create a vector, empty vector or whatever, and then it will now save what you want to save, isn't it? Yeah. So here I was creating a list of a vector. So for each of the 6 vectors, 6 lists that I've created to represent the object name, okay. So when I is 1 here, we are talking about the exponential. When I is 2, we are talking about the next distribution. Okay, fine. So here, so now keep in mind that I'm using double for loops. So it meant that it's not always you'll be using single. You can actually use more than 3 loops at the same time. So in some future time, you see someone using 3, 4 loops at the same time. So look at what I'm doing here. So here, what the essence of the double is not once you understand the single, the double is straightforward. Okay. So for the first for loop, what I'm saying is that for I from 1 to 6, I told you the sequence along up to the names. Okay, it's just giving me indexes 1 to 6. So here, when I is 1 means that I'm considering the first distribution. I think the first distribution was exponential, right? Fine. So here, so it means that if I consider the exponential, okay, for I equals 1 means for the exponential distribution. Now, I'm considering all the k in 1 to the number of replicates or simulation. Here is telling me that for because I told you for each sample or each distribution, we have 100,000 different samples, isn't it? So here I'm finding, so so when I consider I equals 1, I'm considering exponential. Then I'm saying that for the exponential, now find the mean for when the replicate is 1, come and find the mean. So meaning that when I is 1 here is exponential, then when k is 1, find the mean. Then when k, and keep in mind that when we consider I equals 1, it will come and do the second loop, finish all the 100,000 different instances before it starts from I equals 2. Okay, so that's basically what it does. So it means that when it's considered when I is equal to 1, then it come and execute the second for loop, everything the second for loop before it goes to when I is equal to 2. So the very moment we are going to I is equal to 2, then it means we are going to the next distribution. Okay, so basically that's what this does. And then I'm saving each of the 100,000 different means for each probability distribution also as what? In a vector, which I explained here. Okay, so just run this, print it out, be curious, and that's always good with when you're learning programming. Print things out, see what each line of code is trying to do, and then because of time, I'll just move to the next thing. Okay, so here I've now found the means, all the means for, so meaning that I've found the 10,000 different means for each of the probability distributions. So now I'm coming to plot so that we will know whether the central limit theorem was true or not. But I told you that the central limit theorem, now I considered 10,000 different samples, right? So if you come here, I considered, 100,000 different samples. If I increase this to 1 million, we will get better results. If I increase it to 10 million, you will get more, better results, okay? But so meaning that asymptotically, the central limit theorem converges, the sampling distribution of the mean converges to the probability distribution if we do the replication a very large number of times, okay? But bear in mind, there's always a price you pay. The more you increase this, then your computer would also require a lot of computational time, okay? So at the moment, if you do 100, within seconds you get your results. If you do 1 million, it can take about, let's say, 5 minutes before you get your results. If you do 10 million replicates, that will give you better results, but keep in mind that it can take about 10 minutes before you get your results. Okay, and it also depends on how fast your computer also is, and so on and so forth. Fine. So now this is the sampling distribution of the means for the exponential. Okay, so here I told you that that's the essence for the list I was creating. So at the moment, I'm just using a for loop, a single line, a single for loop to get all the distributions, the sampling distribution of the means for each. Now let's look at something, and let's see whether the central limit theorem is making sense here. Have you seen this was a Poisson distribution? But now plotting all the means, okay, the sampling distribution of the means of the 10,000 or 100,000 different means for the Poisson samples, you can see that the sampling distribution is now appearing to look like a normal distribution. For the actual normal distribution, is obvious. For uniform distribution, if you remember the uniform distribution, now see the sampling distribution of the mean is also appearing to be normal. If you look at the binomial too, it's also appearing to be normal. But for log normal, okay, the last time when we checked, we saw that for the log normal and the exponential, they were a little bit skewed. If you look at the actual distribution, so you realize for the log normal, always there's a high frequency when we have small values. So it meant that for it to look like a normal, it has to ignore the skewness. So that's why here, the more it cuts the skewness, the more you get something normal. So it means for the log normal, you can only see true normality for the log normal in terms of the central limit theorem if we increase what? If we increase the number of replicates. Okay, so don't forget that. So that's basically what we are talking about in terms of the central limit theorem performing better as you increase the number of times you are finding the means. Okay, fine. So here as it stands, it appears that the exponential appears to look normal, just that it's not perfectly normal because of how many times we did it. But Poisson normal distribution, uniform distribution, the sampling distribution of the means, and for the binomial are looking almost normal. There are several ways we can test normality of a data. Okay, so another way, so we can use histogram. As you can see that the histogram, the degree of stretch to the left and right can tell whether it appears to be normal. But keep in mind that in order to determine whether a data set is normally distributed, I think there are 3 different ways you can test. One way is to use the graphical approach, and with the graphical approach, I mean you can use the histogram plot. So histogram plot, apart from the fact that it's telling us about and the occurrence or the frequency of each of the numbers, how many times each number is occurring, okay, for us to get a fair idea. It also helps us to tell whether that data appears to be normal, okay? And there's another method called quantile plot. So there's something called normal quantile plot. When I say quantile, okay, what is quantile? So now if I should create a data, let's say a sequence, let's say 2, 5, 8, 9. Okay. So now this is a sample. Let's say a sample that I've created. Let me say a sample. Today we'll finish earlier than so far all the lessons because I'm almost done. Okay, so let's say this is a sample. Okay, now when we talk about a quantile, so the very moment I order this one, okay, or let's say I sort this one. So now if I run the samples, see what we have. So if I run the samples, this one, let me put 9 here, and let me put, let's say 10 here. Okay, so you see this one, there's no ordering. So sample quantile is just ordering your data with, as in ordering it in increasing order of magnitude or decreasing order of magnitude. So now you see initially the sample was 2, 9, 7, 10. The very moment I order my data in increasing order, then the ordered data set is what we call sample quantiles. So it's nothing strange, okay? Just that sometimes in statistics, certain simple things would have some strange names attached to them. It doesn't make it difficult, okay? So sample quantiles is just what ordering ordering your data in increasing order of magnitude, okay? So that is like that's what we mean by the sample quantile. So the QQ plot is plotting the ordered data, and for each of the data, it will have a certain probability of occurring in the context of normal distribution. And that probability is what we are calling as theoretical, as in so there's a formula, you can check what the normal quantiles is. Okay, so that's that part, I think is it the position minus half divided by the size. I think it's I minus half divided by n. I've forgotten a little bit, but I think that is it. So with that, you can also get the corresponding theoretical quantiles. So that's what we mean by the theory. So it means that for each of the samples that has been ordered, for each ordering or for each value, okay, so the I that I said, the I minus half divided by n, the I is the position, the ordered position after ordering. So the first position minus half divided by the size of the data. So if the data was, let's say 30, then you put 30. That will give you, I mean, a form. That's the probability, I think, with which it occurs. Okay, fine. So with that, you can easily find the theoretical quantities, and you don't have to do it yourself. I mean, so this line of code will do that for you. You don't have to worry about that anyway. So fine. So now let's see how to conclude on normality from QQ plot. So if you hear QQ plot, it means quantile plot. But what we are saying is that it's actually plotting sample quantiles, which is just an ordered sample or a data which has been ordered against its theoretical quantiles in the context of what normal distribution. Okay. Now, the blue line is literally the line of best fit. The very moment, so if you look at, let's say, normal distribution, so it's the same data. So it's technically the sampling distribution of the mean that I plotted with histogram to conclude on which ones look very normal. Okay, that's basically what I'm trying to use. So you find out that the KQ plot will help us to know that indeed the exponential didn't look very normal. If you look here, if you look at the histogram, you realize that there was still a little bit of skewness, and this skewness could be removed if we had done the replication another like with, let's say, 100 million times, or let's say 10 million times, then almost everything will look normal. Okay, so at the moment, Poisson is looking normal in terms of the sampling distribution of the mean, but exponential is not very, very normal, right? But the KQ plot will expose it. If you are not very normal, you'll be exposed. Let's start with the normal distribution, the sampling distribution of the mean for the normal samples. Can you see that almost, so the very moment you realize that the plots I'm talking about, after plotting the sample quantiles and the theoretical quantiles, and the line of best fit is all the points are on the line of best fit or are very close to the line of best fit, then it means that that data appears to be normally distributed. So that is basically, so if you look at the sampling distribution of the mean from the exponential samples, you can clearly see there's a little bit deviation from the line of best fit. Like the tails, you see the tails are deviating a little bit. So from there, I can now say that it appears that the sampling distribution of the mean from the exponential samples appears to be not very normal. So it means that we can improve this result by increasing the number of replication. Okay, but for Poisson distribution, if you remember from the histogram was also almost normal in terms of the sampling distribution of the mean. And if you look at the KQ plot, it's doing better, clearly doing better than the exponential, because here almost the upper part is almost on the line of best fit, but it's the lower part that deviates a little bit. If you look at the uniform, it's also almost perfect, right? And if you look at the normal, it's perfect. And if you come down the log normal, you can clearly see. So it means that even if histogram is not able to expose your non-normality, KQ plot will expose you. Clearly, KQ plot is exposing the log normal sampling distribution of the mean from the log normal samples. And you can see the binomial ones are doing well. So it means the discrete ones are doing well. The central limit theorem is doing very well for the discrete distributions. For the continuous distributions like the uniform, and also for the actual normal distribution, we are getting sampling distribution of the mean looking very almost normal. All right. So in future, if you really want to test normality of the data, so the previous two, the histogram and the KQ plot, are two ways of concluding on whether a data appears to be normal. But don't forget that in statistics, we said that you cannot make very vivid or make conclusions with confidence based on just descriptive summaries. So you should always support your descriptive summaries with what? With some statistical or inferential statistics. So it means that in order to conclude on normality, after doing the graphical representation, you can actually go further to do to do actual normality test. Until then, that you can now say the data is normal. Even with this normal distribution, sampling distribution from the normal of the mean from the normal samples, it appears to be very normal from here. It's obvious, okay? But you'll be shocked that you do actual test and for the uniform, because of this little deviation, it might not be normal when you do the actual test, actual normality test, okay? So here, what I wrote here was just to tell you all the various normality tests you can do. If your data is a time series data, there's a test called Jack-Barra test. The data we are dealing with is not a time series data. It's not a data recorded over time. Okay, that's what I mean by time series data. So we don't need the 7. So this 7 is not needed in our case. That's why I added for time series. And keep in mind that for any statistical test or inferential statistic, we have 8 parametric method and 8 non-parametric method. For any statistical model, we also have 8 parametric and non-parametric methods. If you've heard of regression, we have parametric regression models, we have non-parametric regression models. If you talk about ANOVA, which is parametric test to compare means across more than 3 groups or more than 2 groups, okay, we have 8 non-parametric method called Kruskal-Wallis. So for every test you do, or for any statistical model, we have parametric and non-parametric methods. But keep in mind that for the parametric methods are always better than the non-parametric methods if the parametric assumptions are met. So at the moment, in order to, so keep in mind the best statistical test for normality is technically the Shapiro-Wilk test. If you don't know the name, so keep in mind Shapiro-Wilk test is actually the best normality test, but keep in mind that it can only do up to 5,000 samples. So suppose you have a data set and the data set is extremely large, more than 5,000. There's no statistical package or software. If you do it in R, it cannot do more than that because there's actually a limitation based on how large the Shapiro-Wilk test can actually be effective up to. So it can only do up to 5,000. If so, so it means that I could have also tested normality of the 100,000 sampling, 100,000 means for each of the probability distributions. But I couldn't have done it with the Shapiro-Wilk because they are 100,000 for each sample, each distribution. So it won't work for this one. But that is the recommended test for any normality test. And the next one is called Anderson-Darling. And technically, the Anderson-Darling is the second best statistical test for normality that you can always go for. And we also have the Lilliefors or test, and we also have the Kolmogorov-Smirnov test. This KS and test is also very useful. But keep in mind that if your data, and it's also non-parametric test anyway. So the non-parametric tests are useful when your sample size are more than 5,000. So it means that in situations like our case, where we have 100,000 different samples, okay, of the means, okay, if I want to test normality, overall normality, okay, I cannot use the Shapiro-Wilk because the Shapiro-Wilk has a limitation of the amount of the size it can take. Okay, so in that case, I can use the Kolmogorov-Smirnov test, but keep in mind, and the Anderson-Darling test performs better. It has a better power. When we talk about power in statistics, we are talking about the ability for the test to actually reject the null hypothesis when it is true. Don't forget that for normality tests, always your null hypothesis. Keep in mind, we've not done statistical inference. We've not done hypothesis testing. But keep in mind that for any statistical test you do, it has something called hypothesis test, or it has something called hypothesis. And the hypothesis has 2 different hypotheses. One, and the hypotheses are mutually exclusive. So by mutually exclusive, what I mean is that we have something called the null hypothesis. So in this case, the null hypothesis, which is the test you assume to be true until proven otherwise, for the normality test is actually that the data is normal. So, and then if the alternative hypothesis is that the data is not normal, okay? So technically, there are ways of concluding with the hypothesis testing. I didn't do any normality test because I've not started statistical hypothesis. I didn't want to add things. I just want to make it a little bit organized. So at the moment, I didn't do anything on normality test, okay? But we can clearly see that it's only a few that will be normally distributed, because clearly exponential, when I do normality test, it will not, because of the dispersion away from this line of best fit based on the KQ plot, for instance. But something like this might hold, something like this might hold, and so on. But even this, the little deviation here, okay, so keep in mind that the normality might not always be due to outliers. Skewness can also cause the data to be non-normal, okay? So there are instances where anytime the data is not normal, people just rush and conclude that it's because the data has outliers. But the reality is that a data can be skewed, okay, but might not be an outlier. In statistics, An outlier, which we know that is something that is extremely large or small. So if I have a number, like let's say I have 257, and I have a number like 10, like 1,000 or 100. How 100 is so big than compared to the other numbers, so it makes it what, an outlier. But statistically, if I create this range, if I find the mean of all those numbers, and I add and subtract 3 times its standard deviation, I'm going to get an interval where the lower limit will be the mean minus 3 times the standard deviation, comma, the mean plus 3 times the standard deviation. If you create that range, any number that is not within that range is an outlier. So that is actually the most statistical approach of determining a number or determining whether anything is an outlier. So an outlier is any number that falls or is not within 3 standard deviations away from the mean. Okay, so keep that in mind. So basically, this was just to tell what exists in terms of the various normality tests that you can do. But don't forget, the Jack-Barrett test is strictly when you're testing normality of what time series data. Okay, so now quickly to wrap up. So the last thing was talking about Jackknife and then bootstrapping estimation. These estimation techniques are very important. So suppose I gave you a data set. For instance, suppose now we've simulated 100 samples from exponential distribution with rates equal to 2. Now keep in mind that if let's say a random variable or a data follows exponential with, let's say, parameter 2, the mean will be 1/2. So meaning that if anything follows exponential with parameter lambda, its actual mean is going to be 1/lambda. So it means that now we know, so now since I'm simulating from exponential with parameter 2, okay, the true mean of this one is actually going to be half. Now we are going to find ways and means that we are going to use bootstrapping and Jackknife techniques to find the mean. And don't forget that if they said that the true mean for exponential distribution is 1/2, you realize that we couldn't bound it. We cannot say that, okay, it's 1/2, but could it be between, can we add some confidence bound to it? And keep in mind, in statistics, once you do any modeling, you should be able to bound your estimate with some prediction intervals. If you don't put some prediction intervals, you're only telling us that the values would always, the estimate will always be what you gave me. But the bounding it is trying to add some degree of uncertainty around your estimate, okay? So keep in mind that it's always good to add some degree of uncertainty so that you can say that, okay, I am 95% confident that the true mean of the data that I'm considering will lie between this and that, okay? So keep in mind, so that's for confidence interval. So, but confidence interval is slightly different from prediction intervals, okay? So 95% confidence interval is not the same as 95% predictive or prediction interval. The prediction intervals are usually wider than the confidence interval are usually smaller, okay, in terms of its length, okay, fine. So here, after bounding, you rather use predictive prediction interval, and you see how I did it, fine. So here what I'm doing is that, suppose you were given a certain data, you didn't even know that the data was from exponential. Here we have actually used an exponential distribution. For instance, we know its parameter to be 2, and we know that the true mean of this data, if I should find the true mean, that because it's exponential with parameter 2, the mean should be 1/2. This is something, if you're not a typical statistician, you might not understand that, but just keep, it's just a general knowledge. So keep in mind that exponential, every distribution has a parameter. So for exponential distribution, it's characterized completely by its rate or its mean, okay? So exponential with parameter 2, the mean of that distribution would be 1/2. Perfect. So now suppose I obtain 100 samples, and suppose we didn't know that it was from exponential, and we're just giving this sample. Let's say this could have been the weight, or this could have been, let's say, body mass indexes. This could have been anything, okay? And suppose you were trying to find the mean, which you would have done in your normal statistical studies. I mean, your normal research. You were given a data, maybe it could be maybe it could be inflation rate, and you're finding the mean inflation rate. You should be able to bound it. You should be able to say that the inflation rate, the average inflation rate based on your data, is actually this value, but it's between this and that, or it can be anything between that and that. The boundaries or the confidence or the prediction interval around your estimate is only trying to tell us that indeed, even if it is going to change, it will still be something within that boundary. Okay, and that's and it gives people a bit of confidence with your estimate. Okay, so and that's what the bootstrapping resampling scheme, the Jackknife resampling scheme, and another one called and Latin hypercube sampling schemes actually help us to add these confidence or predictive or prediction intervals around our estimate. So suppose we were given this 100 samples, we didn't know whether it was exponential. Okay, so now you are trying to find a mean. You know that the simplest way you could have found a mean of this was just to copy this. So let me simulate this. So the easiest way was just to just create a cell and just type mean around this. That's the easiest thing, isn't it? So it means that this is actually finding the mean. But you realize that this mean is not the same thing as 1/2. 1/2 is because the rate is actually 2, the mean is going to be 1/2. But you realize that even the mean is an estimator. So it means it's not exact. So keep in mind that the mean is another form of estimator. Okay, so that's why when you find the actual mean is 0.51 something. I mean, when you find the mean, but the actual or the true mean is 0.5. But here we see a little bit of decimals. Okay, and that implies that this is just an estimator, which we can check its biasness, whether it's doing well or not. Okay, but with this one, how would you bound it? You cannot bound this one. We know it's 0.51 if we find a normal mean. Okay, if you find a mean, not based on the suppose, because imagine we didn't know that this follows exponential and we're just giving this data set to find a mean. That's what I'm trying to imply. Here we are just stealing a little bit, or we are just trying to cheat a little bit. We are cheating by saying that we already know the distribution is coming from, and we know the specific rate, and we know that its mean to be 1/2. Fine. But suppose that we didn't know this, okay, and then we are finding the mean. This is what you would have done. But suppose you wanted to bound this one with some prediction, maybe 95% prediction or predictive intervals. In that case, you can't do this if you don't use the bootstrapping or the jackknife or the the Latin hypercube sampling schemes to bound it. And basically that's what I'm trying to imply. And you will need it in your future studies, okay? And you can do that so now we are finding the mean of this, and we are going to bound it as well based on the bootstrapping and the jackknife. And keep in mind, you can do it for proportions as well. So suppose that you have, let's say, you did a study of 100 women, okay, and you're interested in the proportion of the women who would give birth to, let's say, males. And you realize that out of the 100 women, let's say 20 of them gave birth to males. So it meant the proportion of male births was actually what? 0.2. But if we consider another set of 100 women, are you sure we are going to get the same 0.2? So that is what we mean by trying to bound your estimate, so that we will say that even though we know that the estimate based on the hour sample for now is 0.2, we believe that for any particular proportion you find, it will be something between these boundaries. And that is the essence of trying to bound your estimate, just to add some degree of uncertainty around it. Okay, so now this is how you would have found the normal means. Okay, so now what is bootstrapping? So now let's explain what bootstrapping sample is and how we go about it. It's so simple. If you already know what I explained from the central limit theorem approach. So for the bootstrap sample, what we do is that, first of all, when you talk about bootstrap sample, it means that they are samples obtained with replacement. Okay, so what do I mean by that? So now, suppose I come here and I create, let's say, some samples. And let's say the samples I'm creating, let's say 1, 4, 8, let's say 3, 9, this. Okay, fine. So now, so this is a sample I've created. So if I should run samples, so this is like a sample I've created. So if I say bootstrap sample, the very moment I use a certain function called sample in bracket, then I put the actual, let me give a different name to this sample so that it doesn't confuse the original function. So let's say I'm using X. So the X is my actual samples, okay? X. Yeah, so the X is my actual samples. So now the very moment I now put this and add, let's say, if I want to select, let's say, bootstrap samples and have a specific size, I can say maybe I want to obtain maybe 3 samples from this. So I'm treating this one like a population, and I'm sampling with replacement. So I can add replace to be equal to true. Now, if I run this one, okay, so now I don't want to be specific with I don't want to select only 3 samples. Let's say I'm sampling everything here, but I'm doing with replacement. So I can just put length of S. I can just put length of X here. Okay, now look at something. So originally, this is the actual samples, okay? It's 14738 0. And now I am sampling with replacement. With replacement means that it's possible I can select 0 and get it again. So as you can see, 0 was selected again, because with replacement, it means that after selecting the first 0, I put it back before I take another sample. And that is what the replace equals true does. The very moment I say false, okay, false, in that case, it's sampling without replacement. And sampling without replacement, you will only see unique numbers. No number will repeat more than one times, but sampling replacement, a number can repeat more than one times. Okay, so you realize that for replace equals false, there's no way you will see a number occurring more than once. Okay, but I am interested in with replacement. Okay, so keep in mind that bootstrap samples is nothing but samples that were obtained with replacement. Okay, so it means that always the first one will be like a population, and then you do some sampling with replacement, and each how many times you do represent the different bootstrap samples you have. Okay, so if I come down here, so what I'm doing is that the last time I told you, if I write for loop, and I could just bring a curly bracket right around it like this. But if it's just a single line, I can choose to ignore the curly bracket, and then it will still work. I can choose to ignore the curly bracket and just write it on a single line. Okay, so here I'm considering all those 100 exponential samples, and I'm considering all the 100. That's why the size is 100. And I'm sampling with replacement. So keep in mind, we want to find the normal mean, but if I want to do it in a bootstrap context or using bootstrap resampling method, this is how we do it. So first of all, your original data will represent your population, and then you now have to obtain about a large number of bootstrap samples. Okay, so meaning that now if I run this one, okay, so here I've obtained so don't forget I'm considering 10,000 different bootstrap samples, means that I'm doing the sampling, and you realize that the sampling, anytime I run, I get different samples, if you remember. So here, or it's now 314 whatever. If I should run again, I get another one, right? So but don't forget, since replace is true, a number can occur more than once. There are instances it might not occur more than once. We don't have a problem with that. But you see something like this, one occurred 3 times because it was with replacement. Fine. Let me where am I? Okay, fine. So here I've obtained 10,000. So I'm doing the sampling 10,000 times. Okay, so that's basically what the for loop. So don't forget, the for loops help us to do an operation a number of times depending on what you specify, the last number. Okay, so here I've done the bootstrap side, the sampling with replacement 10,000 times, but at each stage the sample size is still 100. So here I only extracted the first 10 numbers for you to see that each bootstrap sample is different. So here, so don't forget that here I created a list, okay? And the reason why I created a list was that then each list should save the 100 different bootstrap samples. So basically that's what so bringing one here means that I'm extracting the first bootstrap sample, okay? So if I ignore this one, it will print out all the 100 data sets, or the 100 and the first bootstrap sample with 100 data points. Okay, but here I didn't want to print all the 100, so I just wanted to print the first 10 for you to see that if you look at the first 10 here, and if you look at the next bootstrap sample, the values are literally different. Okay, so it means that we've now, because we want to eradicate any form of biasness. So the bootstrap samples introduces a little bit of what randomness whilst you are still finding the means. And what we are going to do is that for each bootstrap sample, we are going to find the mean for each bootstrap sample. So the first thing is you obtain bootstrap samples from the actual data. How many times? A large number of times. There's no limit on how large large should be. Okay, so here I'm doing it about 10,000 times. Someone can do it about 100,000 times. And if you do 100,000 times, you get better results than 10,000 and so on. Fine. All right, but 10,000 is usually okay. Okay, fine. So here, what I'm now doing is that I'm finding the means of each of the bootstrap samples. Okay, so here too, I'm writing a for loop. And I told that since it's just a single line of code, I can choose to remove the curly. I can bring the, I can run the curly, I can bring the curly bracket, and it's still fine. Okay, but I can also choose to ignore the curly brackets. Sometimes we do that just to scare some people. I mean, suppose someone doesn't know R, when they see something like this, what is happening? Yeah, so keep in mind that you can introduce the curly bracket just to make it neat, but I can remove the curly bracket and write it like this and it will still work. Okay, so now let me run it. It works fine. So here I found the means for each of the Bootstrap samples. Now, after finding the means of each of the Bootstrap sample, the overall mean is what we call the Bootstrap mean. So keep in mind that Bootstrap mean is nothing but, first of all, obtaining a large number of Bootstrap samples from the original data and find the means of each of them. Then the overall mean is the Bootstrap what? Mean, okay? So that's basically, so I've now found the mean for each of the Bootstrap samples. So what this line of code is doing is that it's plotting the histogram. And keep in mind that after doing bootstrapping, the sampling distribution of your parameter, in this case, the parameter is the mean. So the distribution of the parameter should look symmetric, like a normal distribution. If it doesn't look like a normal distribution, it means that your bootstrapping was not done well. Okay, so it means that you shouldn't have, so that's the check. That's what you use to check whether your bootstrapping is doing well. So it means that always, if let's say I was doing bootstrapping for the proportion, after plotting the distribution of the proportions, I should get something that looks like this. That looks like symmetric. Symmetric means that it should look like something like a normal distribution. Don't forget that it's not only normal distribution that is symmetrical. Even T distribution is also symmetrical. Okay, so here we are just saying symmetrical. We are not saying strictly normal, but we are just saying symmetrical. Okay, fine. Just that for symmetrical distributions, I mean, so if the bootstrapping is done large number of times, certainly the symmetric distribution will converge to normal. And for the mean, the reason is because of central limit theorem. Okay, fine. So here I pasted the true mean. I told you that since we knew, we were just trying to do a little bit cheating here. We knew the actual distribution of the data was exponential with parameter 2. And we said that the true mean is 1/2. But when I found the bootstrap mean, meaning that the overall means of all the various means for each of the bootstrap samples that I did. Okay, so meaning that for each bootstrap sample, we find a mean. Then we are going to get a sampling distribution, or we are going to get a distribution of means, right? Then overall mean, just as we're doing, the overall mean now becomes what you call your bootstrap mean, all right? And then when I now find the normal mean of the actual data set, it gives me this. So you realize that even the normal average that we usually find is not technically the actual answer, right? It's just based on the sample you have. So that's why if you just find average of, let's say, height, average of, let's say, weight, average of, let's say, BMI, and you think that average is truly the average BMI for within the population that you, or target population, is not true. So that's why you should always be able to add that degree of uncertainty. And this is the smartest thing you can do, okay? So you can clearly see that the more I was introducing that randomness by considering different bootstrap samples, look at how my estimate is. Now, my actual estimate is 0.5158. But if I do the normal mean, it's 0.5153, okay? Fine. So the normal mean is doing well, but we don't know its prediction interval. But this is going to help us. Okay, now let's come down. So if you come down, I wrote this code. So first of all, the first one is the bootstrap mean. Okay, that's the first line. And the prediction interval is just trying to find the 95th quantiles. Okay, so the 95th quantile will return. So if I should just copy this one and then run this. Okay, so this is what we mean by the 95th quantile, and I treated this in the previous videos. Okay, so this one simply implies that the prediction interval is nothing but trying to say getting the two values such that for the first value, 2.5% of your data set should lie below that value. And for the upper limit, which is the 95.5%, it means that 97.5% of the data set are actually below that value. Okay, so basically that's what the quantiles are, and you can use those quantiles, the 0.95 or 95% quantile, to represent your prediction interval. If I wanted to do confidence interval, I was supposed to consider this mean that I've obtained, the mean plus or minus, let's say if it's 95% confidence interval, I would have considered the mean minus 1.96 times the standard deviation divided by the length of the data, and that will give me the lower limit. If I want to find the upper limit of the confidence interval, I just consider the mean plus The 1.96 is what we call the critical value, okay, for normal distributions, the critical value. For that, the critical value, and then is the critical value when I'm considering significance level of what, 5%. Okay, fine. So basically, if you could have also obtained the actual confidence interval, but the prediction interval is better because the confidence interval will be very narrow in our case. Okay, fine. So when we talk about the bias, so keep in mind that after getting any estimator, it's always good to find its bias. The bias is how much does it deviate from the true value. Okay, so we knew that it was exponential, and exponential in our case with parameter being 2, the true mean was 0.5. So now I just have to subtract the bootstrap mean, as in subtract the true mean from the bootstrap mean. So that difference is what we mean by our bias. And if bias is small enough, something close to 0, then it means that it's doing well. And clearly we can see that our estimate, our bootstrap estimate is doing well. And now this is actually the prediction interval. So this prediction interval is saying that this is the actual bootstrap mean, okay? However, it's something that can be bounded above and below by this interval. And it gives, so if we are doing a study, let's say a publication, and you were able to obtain bootstrap means instead of the normal mean, we were able to obtain bootstrap means with some confidence bound, or with some bound prediction interval. I mean, the journal will be very happy with you. Okay, fine. So don't forget that. And then you can do it for proportions, even so you can actually do bootstrap estimation for standard deviation as well. Why? Just obtain the different bootstrap samples, find standard deviation of each, and find the mean of all the standard deviations, and that is the bootstrap estimate of the standard deviation. So you can actually find bootstrap estimate of any parameter you are interested in. Okay, so for the Jackknife is straightforward. It's actually simple, but sometimes it can even be more effective than the bootstrapping. Okay, and you can see it in this particular study. Fine. So here, so the Jackknife is called leave one out estimation. So this is simple. So what it means is that the original data set, what I'll do is that I'll first of all take the first data point out before I find the mean. So that's what we call leave one out estimation. So it means that if I have, let's say, 10 data points and I want to find the mean, I'll take the first one out and find the mean of the remaining 9. When I'm done, I'll take the second data out and find the mean of the other 9. And then when I'm done, I'll take the third one out, okay, and then find the mean. So that is basically how we use the Jackknife estimation. So the Jackknife risk sampling schemes implies that anytime you find the estimate of, you find anything, take the first data point out, do that, then take the next one, do that. So you do it for up to the last one. And keep in mind in R, so suppose we have our samples. So let's say I'm extracting the first 10 samples of the actual data. Suppose I want to take the first one out. All I need to do is that I just have to bring a square bracket, okay, and just bring -1. -1 will take the first one out. So you see, initially it started with 0.37. Now it's starting from the second one up to the last. The first one is gone. If I want to take the second one out, I have to put -2. And you find out that this is the second number. Now it starts with the first, the second is gone, and it's continuing with the third. So keep in mind that the minus, extracting with the minus of whatever number takes out or takes away that particular position, the number at that particular position. Okay, so it meant that here I'm finding the mean, but for each mean, I'm taking out the ith position. Okay, so that's basically what this is doing. So after that, it meant that finding the means of each of the data after taking one out, okay, the overall mean of that is what we call the Jackknife mean. But the bootstrap mean is the overall mean after you found means of bootstrap samples, okay? And then the Jackknife is finding the overall mean after you found means for each of the data where you've taken one out, okay, across all the data points, you've taken one out, you find the means for each. The overall is your Jackknife estimate of the mean. So you can also find Jackknife estimate of standard deviation. How? It means that if I have the original data, I take the first one out, find the standard deviation, then I take the second one out, find the standard deviation up to the last one, and then finding the overall mean of the various standard deviations is actually your Jackknife estimate of the standard deviation. And then you can also, so when you do that, you can also get a prediction interval. So you can also do the 95%, 95% quantiles, and that will serve as your prediction interval. And you find out that if you plot the distribution, now look at something. So this was a true mean. It was 0.5. So it means that for any estimator to be doing well, it should be very close to 0.5, isn't it? The actual average of the data is 0.5153. I've recorded in 4 decimal places, okay? Basically, that is what the round. So if you see round here, with the 4 here, I'm rounding this number, the number here, to 4 decimal place. So you can follow each line of code and understand what is happening. Okay, so here you find out that the true mean is 0.5. The Jackknife mean was 0.5153, which was actually the same as the average, the actual average of the data. But the good thing is that with this one, I've still been able to obtain a prediction interval of this around it. If you had found the normal average, you couldn't have what added any confidence bound or any uncertainty around it. Okay, so here, so that's the essence of the Jackknife sampling. And from here, you can see that Jackknife is doing better than what? Is doing better than the Bootstrapping. Why? Because the Jackknife estimate is close to 0.5 than this. You see, both are 0.51, 0.51, and but here is 5.3, but this is 5.8. So there's a little bit, but they are literally doing the same thing, right? So you can actually look at the bias of each. So if you look at the bias, so if you want to see the bias, so this is the bias of the Jackknife by subtracting the actual estimate from the Jackknife, considering subtracting the true mean from the actual estimate of the Jackknife, and then, or you can alternatively look at how close is each of the estimates away or close to the actual mean or the true mean, and can clearly see that the Bootstrap the Jackknife is a little bit doing better. I mean, but at this stage, they are doing the same, because here is just 4 decimal place difference that is making a difference. But apart from that, they are literally doing the same. So it means Bootstrapping and Jackknife estimation can equally do better. And there's another sampling scheme which I didn't treat. You can look into it. I did a publication and they expected me to add that one to it. It was a disease modeling paper, one of my papers, and then I was estimating, let's say, reproductive number, that R number or the R naught that I mean COVID-19 has exposed us to. Okay, so I was estimating that with another parameter called Malthusian parameter, and then also infection probability. And I needed to use the Jackknife, the Bootstrapping, and also the Latin hypercube sampling scheme to bound my estimate and find the bias. The bias is just each estimate minus the true value. Okay, so basically that is what I did, and so that's what the journal wanted me to add a Latin hypercube. I forgot, I didn't add the Latin hypercube, and I only did for Bootstrapping. So then the next time they told me to make that correction, I had to add a Jackknife, and I added the Latin hypercube as well to it. All right. So this basically brings us to the end of today's class. So for today's class, what we basically did was just to, first of all, solve some previous questions from last week. So we did a little bit of Monte Carlo estimation, trying to determine the occurrence of birth. And now you should be able to tell me how many even numbers, how many more odd numbers, how many prime numbers, how many any sequence from within a range. You should be able to tell me how many exist, and you should be able to tell me those exact values as well. And you can always use just this line of code, editing it to suit anything. If it is multiple of 8, I only need to change this 12 to 8. Okay, if it is multiple of 10, I only need to change this 12 to 10, and you get everything you want. Okay, and then now we've also exposed S to central limit theorem, and we said that be careful. The central limit theorem is not saying that if your data set is 30 or more, then the data is normal. It never said that. It is rather saying that if you find let's say if you have different samples and you find the means for all the various or all the different samples, okay, then if you try to plot those means, that is technically what we call sampling distribution of those means. Okay, if you plot them with maybe histogram, then that distribution you are seeing is technically going to look something symmetrical like a normal distribution. And if you consider large different samples, then you get something that converges more to normal distribution. But if you consider something small, so suppose you consider 1,000 different cases of the sample, and you try to prove central limit theorem, you might not get something that looks very normal. We saw from the log normal distribution, we saw from the exponential that the sampling distribution of the mean was not looking very normal. Okay, there was a little bit of deviation, even from the KK plot, which is called the quantile plot, and then even from the histogram as well. So keep in mind that if you do the different samples a large number of times, then you get something that indeed converges to normal distribution. And it's very powerful, and most of the parametric methods. And that's why it's very important that before you do a test, you have to decide whether your data set is normally distributed or not. Normal distribution technically is the most important probability distribution. But keep in mind, if you are doing Monte Carlo simulation, then uniform distribution is extremely important because it is what we use to determine when an event should occur. And then keep also in mind that when we are doing stochastic simulations, which we are not going to treat for the whole course, but if you are doing stochastic simulations, specifically continuous time Markov chains, then exponential distribution is very important. My case, when I was simulating the spread of parasite across different locations of a fish, for instance, I needed to use an exponential distribution because the amount of time parasite will stay in anybody location actually follows an exponential distribution. Okay, so in essence, the probability distributions really help us to model real random phenomenon that we see every day. Okay, and then we've introduced bootstrapping, we've introduced jackknife estimation, and here we are saying that it's always good to have, don't just estimate, don't just find means. If you're able to bound your means, then you are trying to tell us that even if the mean for another instance where you collect a different data set, even if the mean is not exactly what you had today, we believe that any future mean you find might be something between those boundaries. And that is why you need to add some degree of uncertainty to it. Okay, so I would end here and thank you very much for joining the class. And don't forget to subscribe. Everything will be uploaded on YouTube. And then please don't forget to subscribe and share. And thank you very much. And meet you next week. Next week, we are going to strictly work on Jupyter Notebook. Okay, next week, we are going to learn how to use Jupyter Notebook to do the kind of things I was doing so that we'll switch from our studio. Let's switch from our studio. Okay, it's not like our studio is not good, but you can clearly see the advantages of the Jupyter Notebook over the R studio. And we'll learn that next week. All right. Thank you very much and take care.